Good morning. Welcome to this talk, DDR crosstalk problems where you least expect them. My name is Jayaprakash Balachandran. My co-author is Hana Bian. We have been working on DDR for a number of years now. And interestingly, we encountered a strange crosstalk phenomenon last year, which is what we'd like to share in this talk. So this is something we haven't expected. This is something came as a surprise because the DDR4 command address bus, where you observe this crosstalk, is really works at a fundamental frequency of 800 megahertz. So here's the outline of my talk. First, I'll review the interconnect I/O trends as well as the memory trends, and then I'll review the DDR functionality, DDR interface functionality from a high level standpoint as required for this presentation. And then we'll get into the meat of this presentation where we'll talk about the crosstalk and the command address bus. So we'll see how the crosstalk is amplified in the command address bus. So basically, using this analysis, we'll derive strategies for crosstalk mitigation. And we'll also derive lessons for DDR5 implementation later half of this year. And finally, we'll summarize the talk. So to understand this interconnect trends, we need to understand what the drivers for this interconnect trends or memory trends. So one of the important drivers for these I/O bandwidth is really the enormous bandwidth required for various networking services. This graph here shows the projection of network I/O bandwidth requirement for various services, networking services. And to understand this graph, let's look at the year 2025, which is about 4 years from now. And the bandwidth required for IP video and global CDN, which is really a proxy for YouTube and Netflix videos, it grows at a rate of about 6.5x from the 2017 values. And and if you look at that, other some mobile IP services or mobile services, that is actually that will be about 35x. Projected bandwidth demand will be about 35x the 2017 values. And again, if you look at the upcoming virtual reality and augmented reality, the bandwidth demand will be about staggering 65x of the 2017 values. So this high, enormous bandwidth demand pushes the interconnect band I/O rates. The next driver for the faster I/O or interconnect is really sheer increase in raw computing power, thanks to the GPU and open domain-specific architectures. The bandwidth demand is going up, and the computing power is no longer the limitation. The limitation is shifting. The system performance is limited by the system level interconnects and not really the computing part. So next, actually, we look at what are the I/O trends are. Like we looked at what are the drivers for this interconnect trends. The one is being the growing networking services, and the other is being the sheer increase in computing capacity or the computing power. And next, we look at what the I/O trends looks like really. The first is, the interconnects can be classified or grouped into 4 buckets. The one is actually the die-to-die interconnect, which is two dies put in a package, either on an organic substrate or a silicon interposer, and they communicate at high data rates. The second one is actually a chip-to-chip interconnect within the chassis. And third class is actually rack-to-rack interconnect, and fourth is memory links. For the die-to-die, it has been actually, this become the trend recently, die-to-die interconnect, thanks to the rise of chiplet-based architectures. So the reach is between anywhere from 1 millimeter to 50 millimeters, and the data rate varies from anywhere from 4 gigabits to all the way to 112 gigabits. And if you take the chip to chip within the chassis, the predominant standard that drives in the computing systems is really the PCI Gen 4. Today, the PCI Gen 4 runs about 16 gigabits. Many of systems shipping today has PCI Gen 4 capability. In a year or two, you will find systems running at PCI Gen 5, which will run at 32 gigabits, and the PCI Gen 6, which is at 64 gigabits PAM4, is in this works at the standards body. Soon, probably it'll take another 2-3 years. We'll be able to see a PCI Gen 6 systems as well. And third, rack to rack is majority of the rack to rack interconnect today is based on Ethernet. The top of the line products implement 56 gigabit Ethernet. And so the last is actually the chip to chip interconnects using memory links. And so that's what we'll focus on this talk, like the chip to chip interconnects. Yeah, so we're talking about the GDDR6, where it requires for very high performance applications like graphics cards, AI engines, and the DDR memories is more for x86 compute, and where you need a very high capacity at moderate speeds. And third class is LPDDR memories, more used in mobile applications. The LPDDR memories are optimized for low power, but interestingly, they also offer a very high throughput as well. So if you look at the DDRs, LPDDR5, it will run at about 6400, and these systems are available today as DDR5. Still lags, but it's probably started for 4.8 gigabits, and then it has a roadmap all the way to 6.4 gigabits, but comes at a later time than LPDDR. And the last class is really the HBM. The HBM memories are they have a really wide bus width, about 1024 bits, and they are really optimized for very high performance. But the capacity is required is moderate, is not very high, probably the lowest of all. And they are meant for integrating on the chip on the as the silicon interposer. So they are more of a die-to-die interconnect. And they offer a very high throughput, very high performance with probably we can say a moderate capacity. And these are used in networking and high performance AI engines. So for the purpose of our discussion today, the focus is on the DDR systems, and particularly we focus on the DDR4 command address bus. So interestingly, the memory systems are evolving. The high throughput requirement is evolving, that you no longer satisfy the bandwidth demand just by using NRZ signaling. So the memory IOs goes PAM4, and this is with single-ended interconnect, single-ended PAM4 type of interconnect. And some of the recent publications points to that direction. The couple of references here. So it's a pretty very interesting for memory type applications. And the third one is actually comes from NVIDIA again, that in the latest RTX 3090 GPU, they have this PAM4 GDDR6X, which actually uses a PAM4 signaling running at 21 gigabits. And if you look at the GDDR6X roadmap alone, that it goes up to 32 gigabits. So the memory IO is really on fire, that the more and more bandwidth requirement. So let's look at the interconnect SI challenges. What are the challenges in general? So far, we looked at the memory trends, IO trends, and then and then we'll also see what the SI challenges would look like for these type of interconnects. So first one actually is a high insertion loss as we increasing the data rate. So insertion loss becomes higher and higher. Many of the serial link systems today, such as PCI Gen 4 or 5, Ethernet, they need a retimer, a redriver, or some sort to make this links work. And the second one is poor return loss. The return loss, again, if you go through multiple connectors or even at higher speed, even a small capacitance in the die, also makes the return loss very poor, and you need special techniques to overcome them. And third is high crosstalk. Again, the density of this interconnects in be in a motherboard or in a package goes up significantly, and because of high bandwidth requirement, which leads to higher crosstalk. So as a result, what's happening is a poor SNR overall, making design these challenges not a trivial task anymore. So these challenges, what are we talking about? So not, it doesn't happen not just at 112 gigabits, like very high state of art design, but it can happen at even at sub 10 gigabits data rate as well. This is what we want to illustrate in this talk. So these SA challenges are important, happens more at higher data rates, but can also happen at even at sub 10 gigabits as well, which you need to be cognizant of. Okay, so we reviewed the I/O trends and memory trends. Let's look at the DDR interface functionality. Again, it's not going to be a detailed tutorial, but I'd like to give you a sense of what is involved in how does the DDR interface functions from a point of view of our analysis, crosstalk analysis. So let's look at the connectivity options, like how does these DDR systems are wired. So on the left side, what you see is a DDR4. And typically, a DDR4 design will implement a 64-bit data path and 8 bits of ECC. And together, the number of data bits will be about 72 bits. And the 72 bits are implemented using 5 DRAMs, each of by 16. And that's what is shown here, the by 16. There are five DRAMs here. And DQ0 to DQ72. And the data path, the DQ bits uses DDR signaling, meaning that every clock you have two data bits, rising edge and falling edge, will have two different data. And the other important thing is a command address bus, which is what's mentioned here, CTL, this command address and clock. And that actually is a multi-drop bus. This bus is connected to all the DRAMs, shared with all the DRAMs in a daisy chain fashion. And at the end of the chain is where you have the termination. The link is terminated with a physical resistor on the board and then pulled up to a VTT voltage. And there is no training involved in the command address bus. All the data, all the command address and control signals needs to be aligned with the clock, the rising edge of the clock. And then more importantly, it uses the single data rate signaling, while the data bus uses DDR signaling, which means the rising and falling edge, you have two different data. In the command address bus, you have only SDR signaling, meaning the data changes only at the rising edge of the clock. So on the right side, what you see is the DDR5 implementation. The DDR5 implementation actually is very similar to the DDR4. Except there's one difference is about the data bus width. The data bus width is actually is implemented as a 32-bit channels rather than 64 bits. So the DDR5 allows to have more channels. So each data bus channel width is about 32 bits. So if you're implementing instead of implementing a 64-bit single channel DDR5, what's typically implemented as 2 by 32 bit, two channels of each 32 bits, and then there will be an 8 bit of ECC. So for each of these channels, together it forms a 2 by 40 implementation, 2 by 40 bit implementation. And so this is actually typical. One could also have 1 by 32 bit implementation as well. So again, the data bus width is actually DDR, and the command address bus. Command address bus is again use a daisy chain topology, point to multi-point. And the key distinction from DDR4 is there is no termination. The termination is all inside the chip. So it uses on-die terminations, just like the DQ bits. And it also uses command address bus training. So since DDR5 operates at a higher data rate, so they implemented the command address bus training feature as well. Single data rate architecture, so just like the DDR4. So with this knowledge, how the DDR4 system is wired, we can proceed further. The key thing to remember is the command address bus is actually point to multi-point and uses SDR signaling, single data rate signaling. And so what we focus on, as we talked before, the focus of this work would be about DDR4 command address bus signaling. And let's look at the DDR4 5 pinout. So what's the DDR4 pinout looks like? And again, this is also important to understand as we progress further with the analysis. And so this is the pinout. What's shown here is actually for a by 16 device. And the top side, where I'm pointing out here, these are all data bits. The 16-bit data bus is actually put out here. And where I marked with yellow, the bottom is where the command address bus resides. And you can see it's very densely packed in the package. And the column 4, 5, 6 are not populated; they are left empty. And whereas 1, 2, 3, and 7, 8, 9 are populated. Especially, you can see the command address bus being densely populated. And so the package would typically uses a 0.8 millimeter pitch BGA ball for the DDR4. For DDR5, so the JREC rules don't permit me to show this pinout as it is. You may want to refer this JREC standard, DDR5 JREC standard. But essentially, it's the same. It's pretty much similar. It's not exactly same, but pretty much similar. But one key distinction is the number of command address bus, the number of signals in the command address bus is reduced, probably about 8 to 10 signals fewer than what is implemented in the DDR4. So otherwise, it's pretty much similar. So let's actually get in the real meat of this presentation, that essay analysis on the command address bus and the crosstalk amplification effects. So before we go into details, let's understand what are the simulation challenges when we are implementing the DDR, analyzing the DDR signal integrity on the DDR channels. What are the simulation challenges? The first one is setting up the topology itself. So the setting up topology of the command address, read and write, these are different have different topologies, and they need to be wired. And the test bench needs to be created for different use cases or different topologies. And if you consider a 64-bit or an 80-bit bus, a large bus, it's actually, it takes some effort. And it's pretty much it's time consuming to wire to do this test bench, and it's pretty laborious. The second challenge comes with the simulating with the S parameter models. So you go and extract the channel models, be it a package or PCB, and typically the command address bus, even if you consider a few bits, since it's a multi-drop bus, the number of ports quickly will expand. Right? If let's say if you consider a 4-bit command address, just the 4-bit alone, you will end up with about 28-port model, very large. So if you have to imagine that if you have to simulate a very large number, let's say 32-port, 32-bit, 64-bit, this is quickly the S parameter model size will explode. And the problem is not just with the large S parameter models, but also we need to ensure passivity, causality, and the DC point extrapolation issues. If there's the passivity and causality issues are violated, even the DC point, the simulation results will go obviously very erroneous. And sometimes it's easy to detect because it makes a large error, and you can quickly see this in the simulation. Sometimes it makes a very small errors, which are very difficult to track. So especially if you're operating in a very thin margin, doing a good simulation is accurate simulation is something very important. The third one is stimulus data patterns. So especially if you're analyzing the DDR and crosstalk in particular, the data patterns are pretty important. So in some patterns, you won't even see a crosstalk. In other patterns, you will see the complete eye closed. So setting up the right data patterns is important. And you need to have a simulation environment where you'll be able to change the data patterns quickly and easily and manipulate that. And the fourth one is simulation time. And again, we're talking about very large number of ports, and simulation time is especially important. And you don't want to wait for a day to get simulated. And if you want to iterate anything, then it kills the time. So the simulation time is extremely critical, and faster it simulates, the better it is. And finally, the validation of the results itself. How are you going to validate the results? So you need to compare the validation of results. Typically, compare a mask or a specification with the standards, and you need an easy way to compare and validate the results. So these are the few challenges that you will encounter in doing the DDR simulations. Looking at this all challenges, we put together this flow. For this, at least for this particular work, we followed the flow that what is shown here. We typically start with the package PCB layout based on Allegro BRD file. And if it's case of package, it will be an MCM file for the controller. And for the memory cases, it typically comes from the memory vendor. And then you do the X parameter extraction for channel model. In this case, we used power SI. And excuse me. And then we once the S parameter model is extracted, we do a broadband model fit. This is to avoid any S parameter issues, causality, passivity, and the DC point issues. We do a broadband model fit. And then we take this, once we fit in the broadband model, we take the SPICE file. It results in a SPICE file, HSPICE compatible. And then we take the SPICE file into a time domain simulator. In this case, we use system SI. And then we also get this IBIS models for the controller and as well as the memory models. And together we take it and simulate in time domain. Again, there are essentially there are two types of time domain simulation. One is SPICE simulation, just like what is typically called as a transient simulation. And the second one is a channel simulation. Channel simulation can simulate a large number of bits in a short time. It's based on impulse responses to characterization. And there are two types of time domain simulation, channel simulation. One is actually a statistical analysis. Second is bit by bit analysis. For this particular work, we actually we use transient simulation. So we'll not go into time domain simulation. Channel simulation. Channel simulation is more required for if you're doing a DQ bit analysis. At least for this particular work, we use the transient simulation. And then once you actually get this time domain data, the I data, we compare that with I mask based on JEDEC specifications. And if the idea is these I masks need to be met. If the I mask specifications are not met, we go back to the layout and tweak. And if it's met, we release the design to the fab. So that's the flow that we are using for this work. And so let's look at the test bench. How does it look like? This is the system SI test bench. And what you see here on the left is the controller IBIS model. And then followed by a package, controller package model. Again, this is actually a SPICE subcircuit. This is not an S parameter model. This is actually a broadband fitted SPICE model. And then it followed by a multi-port PCB model. Again, this is actually a broadband fitted SPICE model extracted from S parameters. From this, and then from the PCB, it connects to the memories. There are 5 memories corresponding to the 5x16 that we looked at in the previous slide. And then on the bottom side, what you see here is actually the termination. This is the termination you see in the command address bus. And we actually terminate discretely in this test bench environment rather than on the PCB itself. And then so finally we have this VRM that powers this termination, that provides the termination voltage. So bringing out this termination will allows us to experiment. We want to change the values of termination to fine tune the margins. This would allows us to experiment. So another way to do this is this termination can be part of your layout itself, and you can extract. That does not have the freedom does not give you the freedom to change these values. So this is our test bench, and the data rate for this will be running at 3.2 gigabits, which corresponds to a CA bus rate of 1.6 gigabits. The CA command address bus runs half the DQ data rate, 1.6 gigabits, and we use PRBS 15 and 23 patterns for different uh, address bits here, and we'll use it, as I said before, we'll use a transient simulation. One of the highlight in this test bench is actually the wiring between them. So wiring between them is what I call as a vectored connection. You don't have to individually wire each one of these pins. So you can actually connect them, and then you can actually set how many where, which bit is going where, connecting to what. So this, I find it very, very easy to connect, especially if we're working for a very large number of big S parameter matrix or connectivity matrix. This approach, the vectorized connection, makes it a lot easier to work with. And if you want to change anything, this test bench can be put together in 5 minutes if you have all the components ready. Okay, and so next we'll talk about the command address bus I specifications. So we talked about the JEDEC I specification here, I mask specification here, and that's what we'll cover here. And so what essentially what we need to look at is at the clock rising edge, the command address bus, what is the I width and I height looks like. And JEDEC typically calls it as TCL VW, which is VW standard valid window, and same thing as the voltage VW. So the DDR4 specification specifies this command address bus mask. But interestingly, the DDR specification JST 79-4, which is actually for DDR4, does not have this specification, does not actually specify the command address bus mask. So but this is actually specified in another specification meant for the DIMM buffers, JESD 8231 has this mask. For the purpose of this work, we actually use this mask for command address bus. The DDR5 also has similar mask specified. Again, in the case of DDR5, you can find the specification in the JSD 79-5, which is the DDR5 spec itself. So DDR5 actually done a good job of specifying the command address bus mask, unlike in DDR4. And but in the split of JEDEC, I won't be able to show that what the numbers are, but you are welcome to see look at the JEDEC specification. So let's look at the simulation cases, what you want to analyze. The first case, what I call is a case T3, and the second case, what I call is a case T12. And the difference between is actually the length of the via, the length of what is called as active length of the via. In the first case, the case T3, the via length is pretty short where it connects to a DDR signal. So the signal comes from the controller, and then the top layer T3, we connecting this and then connecting to the memories. And this via length is what from the controller to from the top, layer top to the T3 is what we call as active via length. This is where I'm pointing here. And then and the bottom is all stub. And stub is not really an issue in this case because we're talking about a very low frequency, the 1.6 gigabits of data rate max, which has a fundamental of 800 megahertz. And the total PCB thickness is 93 mil. Again, depending on what board thickness you're using, the results can vary. And this is what we use in this case, a 14-layer PCB. And on the right side, what we have a case T12, where the active via length, where actually the signal travels, is actually pretty high. It's probably about 80 mils in length, and this is about 15, 20 mils in this case. So these are two cases where we'll be analyzing the command address bus and comparing with JEDEC mask. So the first, the case T3 is somewhat benign. And you can see here that if you if you extract the model, S parameter model, fit it into a SPICE, broadband SPICE model, and then run this time domain analysis, and you can find that the margins are pretty good. The I is pretty much open except the mem0, the memory 0, where you can see there is the I is not as wide open as the other memories, but still it meets that I mask specification. The I mask is provided here in between. Still it meets. So, I mean, this is something expected because the memory 0 has got the longest stub. The memory 0 and the transaction is going to the memory 0, and you see a long stub to the termination. And that's why you see this reflection. These are all reflections, and that's why you see that the eye margin is not as good as that what you can find in the M1 or M2. Nevertheless, is actually the case T3 meets the eye mask requirements and can run at the specified 1.6 gigabits sub data rate. The other thing to notice in this is actually if you see the eye, you can see different colored traces. So in this case, yellow, green, and then pink. And these different colors represents the different address bits used in simulation. All of them are overlaid one on top of the other. So you can look at a very concise, precise information. So let's look at the case T12. So let's do the same analysis where you have active via length about 80 mils or so. And if you look at that, interestingly, that the eye mask is completely closed. So you don't meet that eye mask specification. You can see here the eye is closed here, and the MEM3 is actually the worst. The eye is closed in multiple ends, and memory 4 is also closed. So this is where we have issues. If you're routing in T3 layer, top layers, the shorter active via length, you can easily meet the specification. Whereas with the longer active via length, your eye is closed. So is it initially when you looked at this, we thought it's really a reflection problem. So is it really a reflection or crosstalk? How will you know then? So let's look at that. So in our initial assessment is really the reflection. But the question is it a reflection or a crosstalk? To assess that, so what we did is actually we used we turned on only one bit. So the eye diagram shows here for different aggressor cases. There are 4 bits used in this simulation. The first case, there is the A4 bit, only one bit is turned on, and all the other bits, and 3 other bits are turned off. So they are the victims, and only one bit is actually active. And you can see here that waveform is actually pretty improved. The eye is pretty much open in all the cases if you have only one bit turned on, one address bit turned on. And you can also see that the impact of the crosstalk. So there is some noise here. And these are the other bits in the bottom. And now if you turn on this, if you look at the second row, the one aggressor case, and you can see here that again, the eye is somewhat is growing. That eye the jitter is actually increasing, and with one aggressor case and 2 aggressor case, it's even more. So the eye jitters are actually increasing even more, especially the vertical jitter, as you can find. In the 3 aggressor case, the eyes are completely closed. So there's no margin here. The eyes are closed. So this actually illustrates the impact of the crosstalk. So first we ask the question, is it reflection? We don't know if it's a reflection or crosstalk. By turning on and turning off the different bits, we can see there is somewhat correlation to a crosstalk. It's not just a pure reflection problem. There is also a crosstalk impact to that. So as they turn on the aggressors, the eye the closure is very progressive. With all the 4 bits turned on, the eye is completely closed. So this is actually a zoom in of the one particular case with and the MEM3, where you find the worst case eyes. And you can see here, this is 0 aggressors. You can see this particular effect is purely reflection, right? You can attribute this or all purely reflection. And with the 3 aggressors all turned on, this actually is complete closure. This is actually, can be crosstalk. This is what we call a crosstalk. But there is also some contribution from the reflection as well. So let's investigate further whether it's reflection or crosstalk. So we looked at the layout. So let's look at the layout of this implementation. How does it look like? In the case of layout. So in the 4-bit, we are considering for the purpose of analysis here, you can see it's coming from the controller and then is routed as a daisy chain on every memory bit. And each of the via points you see here as different memories, and they are routed in a daisy chain fashion, and then goes to a termination, which is not shown here. This is a zoom, closer view of this, the vias. And you can see here the vias they're placed next to each other, and the different address bus A2, A0, and A4 are routed stacked on one on top of the other. The reason why we have this kind of route pattern comes from the DDR pinout. If you have a DDR, if you look at the DDR4 pinout, this is very densely packed. The command address bus is very densely packed, and when you're routing in a daisy chain fashion, that's how it comes out to be, right? And you can also see there are no ground vias adjacent next to each other, and because there's no the grounds in this particular memory pinout pattern, and then it's routed as it is in the JEDEC pinout. So this is definitely prone to crosstalk, but what is surprising is, can this crosstalk happen at 800 megahertz? Is that severe enough to close the eyes? Let's look at this even more carefully with one aggressor case. And if you look at the one aggressor case, and you can see here is a victim noise. If you plot this victim, there are the highest amount of noise induced. This is what it looks like. And if you zoom in closer, and you can see here the peak-to-peak noise is about 320 millivolts. So which amounts to about, if you assume there's about 1 volt of noise is 1 volt of signal swing is present, and it represents about 36% coupling. The noise coupling to the victim, the crosstalk coupling to the victim, is about 36%, which is rather high at this frequency at 800 megahertz. So what is happening? So what we did is we looked at the frequency domain. So if you look at the frequency domain, you can actually get an estimate of crosstalk. So this is what after extracting from power SI, this is what the crosstalk parameters look like. So the blue curve has the one which is actually has the highest amount of coupling, which corresponds to memory. All this the curves are extracted for memory 3 address bits, and you can see the blue curve where the one has the highest crosstalk, and the fundamental frequency lies about 0.8 gigahertz or 800 megahertz, which is actually pretty close to about 38 dB, 37 or 38 dB, which is actually practically the crosstalk there's not much crosstalk there. And if you look at this, the 1.6 gigahertz, the harmonics, like first harmonic and then the second harmonic, which is 2.4 gigahertz, since there is not much signal attenuation is here, see these are very low frequency, the insertion loss is pretty low, so there won't be any attenuation. So we kind of postulate that even the harmonics is getting coupled, and that impacts the eyes. So if you look at the different coupling from this curve, the maximum amount of coupling noise, you can see at 0.8 gigahertz, you have only about 2% coupling, and 1.6, 4%, and 2.4 is about 6.8%. They are nowhere closer to the adapter for 36% what we saw. So there is a large discrepancy. How does this, the noise that we observe in frequency domain so low gets amplified so much in time domain? That was really a puzzling question in our minds. So what we think is actually, after looking at this, intensely debating on the performance of this interconnect, what is the reason for this crosstalk? We think that, in actual DDR implementation, there's not 50 ohm termination. All this DDR, the memory 0, 1, 2, 3, the memory ports are not really terminating 50 ohms. They have more high impedance. Whereas if you look at the S parameter based analysis, they assume all 50 ohm termination. Right, so there is some differences there, and these 50 ohm termination can attenuate some of the coupling noise. So that can contribute one. The other thing is actually there is also reflection happening, since they are not unterminated systems, and the termination is only at the far end at one point. Then the reflections can happen in between, and these reflections can bounce back and forth, and they can constructively add up and can amplify the crosstalk. So this was our hypothesis, that no, there is a reflection happening. These reflections bounce back and forth, and then eventually it amplifies the small, even the 6% or 2% coupling get amplified to somehow to 36%. So how do we test this idea? How do we is really indeed is happening. So one of our thoughts is actually what is the source of this reflection? The board we cannot do, the stub length, those things we cannot control because it's by topology they are fixed. So one thing we could do is really we can actually the other source of reflection is really the parasitics of the DRAM package. The DRAM package has got an RLC or some kind of parasitics that actually can contribute to reflection as well. So what we did is actually we turned off, we removed the parasitics from those simulation, assuming an ideal package, and see how the response look like. Sure enough, to our surprise, that if you remove that RLC model, if you don't consider the RLC models of the package DRAM memories or the package models of the DRAM memories, your eyes actually is pretty much open. So what we saw earlier, the eye is closed, the eye is open, and so the reflections actually they indeed get amplified. The theory is that as at each memory locations, the package parasitics causes a lot of reflections. And the crosstalk noise, however small it is, gets amplified eventually and cause the eye closure. But removing the package parasitics actually can give us the reflections are minimized, and therefore you get a very good eye opening. Right. So again, this is partly interesting. Depending on the package model, depending on the package that you use, your results can completely vary. It's very unpredictable. So you need to use a correct package model to arrive at these results. So looking at the DRAM package models, and you can see here, this is actually from the IBIS file. And you can see here that the inductance of the DRAM package model is about 2 nanohenries, which is really high. And then package capacitance is about half a picofarads, which is okay. But the inductance is rather high, which is what is contributing to the reflections. Yeah, very strong reflections. So we understand so far, we did this command address bus analysis, but in two cases, one is actually a T3 with shorter active via, and one case, the longer active via, about 80 mils. In 80 mils case, we have a complete eye closure. And the eye closure is due to the combination of reflection and crosstalk. And we saw that how the DRAM package models or DRAM package parasitics play a role in this crosstalk amplification. And so what strategy can be used to mitigate this reflection-induced crosstalk, reflection amplified crosstalk? So that's the next step. So if you look at that, if you observe the waveform and the T-tail routing that we looked at earlier, that as we increase the number of aggressors, the eye starts closing more and more, right? Progressively, the eye deteriorates. So one strategy is if you reduce the number of aggressors, then we can definitely improve this, mitigate this cross effect. At least we can meet the JEDEC eye specifications. And the second part on the right is actually the T3 routing. If you see the other strategies, if you reduce the length of the active via, that's the best situation. That dramatically reduces the crosstalk effects or reflection effects. So again, we can employ these two strategies. One is actually use shorter vias as much as possible. And if you can't do it, especially in case of DDR4, it won't be possible to use shorter via all the time because we have a large number of address bits. And typically you need at least 4 layers to break this out, the command address bus. And so in that case, you need to reduce the number of aggressors. So, so how do we actually reduce the number of aggressors? So, so first is our strategy is due to the high number of command address signals, it's very hard to isolate them. But what we can, on the left side, what you can see here is the pinout as defined in JEDEC using via impact kind of structures, breakout structures. The yellow lines here are the command address bus with respect to the original JEDEC pinout. On the right side, what you see is the breakout pattern, what we suggest and what we used for to mitigate the crosstalk. And you can find here, that's actually all shown here in the pink for the command address bus. And what you can find is actually use a dog bone pattern. Using the dog bone pattern, the advantage is you can actually control the spacing between the vias, and to such that there are no more than two aggressors. I mean, one aggressor per bit. So for a given address bit, there will be only one nearby aggressor, right? And then you can introduce. We also could introduce also the ground shielding vias in between, right? So by positioning these vias with the dog bone allows us to position the vias top and down. So that allows us to maximize the distance between the aggressors, and the number of aggressors is limited to one, right? And all the in situations where you have a lot of the vias that comes close together, the right and the or in this, if you can look at the S parameter where you have the worst case crosstalks, then those nets are actually routed in the topmost layers where you have shorter via lengths. The ones where we have less critical, I mean, the vias are actually spaced apart. They can actually, or the aggressors are spaced apart. They can be allowed to route on the bottom layers where with a longer active via lengths, with the assumption, with a condition that um, number of aggressors is limited to one. So you can actually go and follow this pattern in detail, and you can probably derive your own pattern as well. The key condition is to limit the number of aggressors to one and maximize the distance between the aggressors. And now if you can see here, if you do the same analysis, and now you can find a very clean eye. And now this time we included the DRAM package parasitics as well. And this is this is a real channel as a real condition as you find on the actual board. And with the pattern, DDR pattern rewired, the breakout pattern rewired, and also the layer, actually we also modified the layers, which layer what signals go is also modified based on the crosstalk. And you can see here that the eye is pretty much open and we have an excellent margin. And the worst case being again still MEM3, you have a crosstalk, or the reflection, more crosstalk, or the eye is more distorted, but still it has an excellent margin that you can meet the JEREC specifications for high volume manufacturing. Right, so that comes to the lessons learned for DDR5. So what are the lessons we learned for DDR5 based on the analysis, command address bus analysis we did? First is actually always route the command address bus, the topmost layers. Don't route in the bottom layers with shorter active via length. And in this case of DDR5, there are about 8-10 signals fewer. The command address bus is actually uses a encoding scheme encoder similar to the LPDDR5. So the number of command address signals in DDR5 is fewer. So take advantage of that and never ever route in the bottommost layers. And if you have, if you have to route in the bottommost layers by, for some reasons, you make sure that you have a good breakout pattern, right? Irrespective of that, I think you should have a good breakout pattern and with the ground vias, and don't use actually really the VPO structures, via pad. You should use a dog bone type of structures that mitigates the crosstalk effects or the number of aggressors. And the other important thing is actually you should use the right package models. For instance, you'll be using a package model that may not be reflective of your actual product. So this is probably a placeholder, right? Maybe good for initial simulation, but for final validation, make sure that you have the right package models, because that can have a dramatic impact depending on the package model that you use, the memory product that you have, that can make or break your results. And the other thing is actually the command address bus does not really, for the DDR5, that the command address bus is, the frequency operation is higher than of the DDR4, and there are no equalization available. The DDR5 standard specifies DFE, 4-tap DFE for the DQ bits, but there are no equalization available for command address bus. So you need to ensure the good SI by design. So always simulate. So one strategy is you can go by design rules, best design practices, But to avoid surprises like what we are seeing, is better to simulate and ensure the design. Yeah, so these are some of the lessons learned for DDR5. The key thing is actually route the DDR5 command address bus, the top host layers with fewer vias, and work out a good breakout pattern before you start routing the design for the DDR5. So that takes us to a summary. So in this presentation, we reviewed the high-level trends in I/O, interconnect I/Os, and memories. And we saw that the memory speeds are going up, memory I/O speeds are going up higher and higher. And some of the memories, advanced memories like graphics, GDDR6 implements even PAM4 signaling on a single-ended interconnect. So so the memories are something is used from kitchen appliance to all the way to high-end data center servers. And so designing these interconnects becomes, memory interconnects is very critical. And we analyze this crosstalk on particularly on the DDR4 command address bus. And these crosstalk effects, although its coupling is really small, the crosstalk noise gets amplified through reflection. So the conventional analysis, the S parameter, does not clearly explain, but by looking at the RLC parasitic turning off and turning on, we can understand this reflection is what is amplifying this crosstalk noise. And we cannot ignore the DDR package parasitics. And we also discussed the strategies for command address bus crosstalk mitigation. And we also looked at some of the lessons that we can apply when we're designing this DDR5 systems. So the key takeaway is really never underestimate signal integrity at any frequency. So this is something important. People think that signal integrity at 56 gig, 112 gig is very important. In fact, designing at 56, 112 gig is pretty straightforward, because if you go by textbook design practices, you will get it right. Whereas if you look at the multi-drop buses like the DDR4 running at very low frequency, that's where you'll have most of the problems, and never underestimate similarity at low frequency as well. So thank you for your attention.